Math 3 Lesson Summary Video, Madison's Square Garden. This is a practice understanding task, which takes concepts you have been working on and applies them to new situations. The purpose of this lesson is to use proportional reasoning to calculate the ratio of arc length to radius to define a constant of proportionality for any given angle intercepting arcs of concentric circles. Madison has only marked the degree measure on the arcs of the outermost ring of the garden. Determine the angle measure for the arcs on the inner and middle rings of the garden. So we have our arc measures. Think back to the first lesson this unit when we talked about arc measure and how it's always a reference to the central angle. So if the arc measure of this outermost ring is 60 degrees, then its central angle is also 60 degrees. But if the central angle here is 60 degrees, that means that the arc measure for this small arc is also 60 degrees, and the arc measure of this middle arc is also 60 degrees. The same can be said about all of these other angles. If their arc measure is 50, the central angle is 50, which makes the other arc measures 50 as well. These would be 40. These would be 120. And these would be 90. Madison needs to order pavers for the garden. She plans to vary the size and color of the pavers in different parts of the garden. Consequently, she needs to know the lengths of the different portions of the paths. Help her to complete this table by calculating the missing arc lengths. Yesterday in class, we determined that we can find arc length using a common formula, or a common ratio. If we know what that n degree is to measure that arc measure or that central angle, we can set up a fraction that we're going to multiply by the circumference. So for our 40-degree sector, that fraction is going to be 40 over 360, which happens to reduce to 1/9. For the 50-degree sector, it'll be 50 over 360, which reduces to 5/36. 60 over 360, which is going to reduce to 1/6. 90 over 360, which reduces to 1/4. And 120 over 360, which reduces to 1/3. So these are the ratios that we want to multiply the circumference by. If we can find the circumference of the 10-foot radius circle, the 20-foot radius circle, and the 30-foot radius circle, it's just a matter of multiplying by those ratios to get our arc lengths. So don't forget your circumference formula, which is 2 times pi times the radius. So for the 10-foot circle, our circumference is going to be 314.16 feet. For the middle circle, it's going to be 1,256.64 feet. And for the outer circle, it's going to be 2,827.43 feet. With our total circumference and our ratios, it's just a matter of filling in our table. I'll do 40 and 50, and you can finish the rest. For the 40-degree sector, the 10-foot circle is going to have an arc length of 34.9 feet. The middle circle will be 139.63 feet. And the larger circle is going to be 314.16 feet. For the 50-degree sector, it's going to be 43.63 feet. The middle, 174.53 feet. And for the outer, 392.70 feet. One thing Madison noticed involved the ratio of the arc length to the radius of the circle. Complete this version of the table and state what you think Madison noticed. So if we look at our information from our chart above, we're looking for that ratio between the arc length and the radius. So our radius is 10, 20, and 30 feet, and we just found the arc length up in the table above. If we do that ratio or that division, we end up with 3.49, 6.98, 10.47, 4.36, 8.72, and 13.09. You can finish the rest on your own. What we're trying to see is there a pattern that we notice that's consistent as we go along? One of the things that I notice is that if this is 3.49, 6.98 is twice that. And 2 times 4.36 is 8.72. It looks like the ratio for the 10-foot is exactly half of the ratio for the 20-foot. This would make sense since 20 feet is actually twice as big as 10 feet. Does that work for the 30-foot? 3 times 3.49 is 10.47. It seems to be consistent. These ratios are proportional to the difference in the radius. Another interesting ratio to look at would be to take that arc length and instead of creating a ratio with the radius, create a ratio with the circumference. Create a table of your own and go through and take all of your arc lengths and divide it by the circumference. See if you notice a pattern between those ratios.